Two vertical forces are applied to a beam of the cross-section shown. Determine the maximum tensile and compressive stresses in portion BC of the beam. Okay, so let's see, in portion BC right here, we know if we were to draw, say, a shear diagram, how would that look? Well, let me just make this a little bit longer because I'm going to put a moment diagram as well. So this is going to go all the way down like that. And let's say first I want to plot the shear. So we'll say this is the shear diagram. This is V in kips. And this is our x-axis, right? So we know that the shear, here it's going to be 25, positive 25. Then here it's going to be 0. So let me change color just to make it clear. So we are going to get positive 25 until here. Then we're going to get to 0 right away because these are point loads. Then we're not going to have any shear inside. This is impure bending. And then we're going to have a negative shear pointing in, and I just want to make sure I'm doing this correctly. So then we're going to have a negative shear, right? So right right here, and right here, and back to 0. Right. So this is going to be what? Well, this is going to be 25 kips, and this is going to be negative 25 kips. Now, why, you might ask, why is the shear here positive? Well, here, if I make a cut here, I'm going to need a force here to balance it. And then once I get to here, I don't need that anymore because here I have this and this, right? But what about once I get to here? Well, once I get to here, I can kind of do a similar thing. Actually, I don't know why this should be the way it is. So I'm probably going to ask that. Ask why shear changes sign. It's something to do with the free. So if I cut here, I'm going to have this force and that force. So that would be, I won't have a shear in there. But if I cut here, then I'm going to have a shear going down, which we represented as up. And then if I cut here, then I'm going to have a shear going up that is still opposing. So it's kind of the, so if this, we represented this as positive shear, then this has to be negative. So that's kind of how it is. I'm going to ask for more clarification, but that's how I'm thinking about it now. So now, and I'm sorry if I don't have a better answer. So now we're going to do the moment diagram. And here we're going to have our x again, but now this is going to be our moment. And so our moment is going to have units of kips times inches. And so it turns out the slope is going to be, the 25 is going to be the slope because we know that dm dx is equal to dv. So the slope of the moment function with respect to x is equal to dv. So if we keep that in mind, then we would know that this is going to have a slope of 25 until we get to 20. So if it has a slope of 25, kips per inch. Kips times inches over inches, and we multiply by 20 inches. Then we're going to get here a value, I think, of 20. Let's do 25 times 20. So that's going to be 500 kips, if I am correct with my work. Or maybe not. Let me just double check. 25 times 20. Yeah, 500 kips. So that's right here. And notice how here I'm starting to keep this flat. And why am I keeping this flat? Well, because here we just said if we cut here and we represent this as a force, they're equal and opposite. So I don't need any force, any shear in here. That's why it's pure bending. And so the moment doesn't increase. It's a pure moment. It stays at 500 kips, and then it goes back down to 0 because this is symmetric. So here we're going to get to this point right here. Let me do it nicely, just like that. And so that's going to be, I'm going to do it better, 500 kips inches right here. And so once we have that, we know what the moment in that section is. So we can find the maximum tensile and compressive stresses once we analyze a little bit what's going on. So let's think about this. Let's say that this is my y-axis and that this is my x-axis right here. So that's my y. So my z, using the right-hand rule, is going to come out from there. I think I did another video where I kind of messed that up. I didn't specify that our z-axis had to be found with the right-hand rule because I did the graph from the right instead of from the left. But for now, this should be okay. So now think about if you look at your cross section, this is where your x is going to come out of. So this will still be your y, and I'll do it from here. This will still be your y-axis, but this will be your z-axis. So it's important to keep that in mind as we do these problems. Now we want to find the stress in that portion. Well, how do we do that? Well, we know that the stress in that portion for pure bending is going to be the moment, which we just found, the moment times the distance from the centroid and a negative in front divided by the moment of inertia. So we need to find what y and I are. And to find what y is, let's leverage some symmetry. We know that this is symmetric about this axis. So we know that the centroid is going to be there in terms of z distances. But what about our neutral axis? We know that this is a composite shape, and so it has different centroids. It's got the centroid for the middle the middle rectangle, the centroid for the bottom rectangle, the centroid for the top rectangle. And we know where these are. Based on the information that they give us, we can figure those out. But now to find the actual y of the total centroid, what we're going to do is we're going to take the area of each. So let's name this 1, 2, and 3, and these are going to be cut right here. So let's say we're going to take the area of 1, and that's going to be 8 inches times 1 inch, and we're going to multiply it together. And then we're going to multiply it by my y coordinate of the centroid for that specific rectangle from this z-axis that we drew over here, which is not the z-axis of the datum. It's kind of like the datum. So, or datum. I don't know how to say it. So it's going to be this distance, essentially. So we know that the center is going to be halfway from 1 and the height. So it's going to be 7 plus 0.5. So that's going to be 7.5 inches. That's right here. So that's my area. I just want to make sure you understand that this is the area, and I also want to make sure I understand that I'm not making any mistake. So that's the area, and then that's the y coordinate with respect to a z that's at the bottom. Now, we're going to add what? We're going to add the area of the middle rectangle, which is 6 times 1. So 6 inches times 1 inch, and that's going to be, and multiplied by the location, the y location of the centroid, which is going to be 3 plus another 1. So that's going to be 4 inches right here. And then finally, we have one more shape. So that has a base of 4 and a height of 1. So that's going to be 4 inches times 1 inch. And then we multiply it by the location of the y for its centroid, which is 0.5 inches. Now we divide by all the areas. So that was area 1. This is area 2. This is area 3. And now we divide by area 1 plus area 2 plus area 3. So that's going to be 8 inches squared plus 6 inches squared plus 4 inches squared. Okay, so now we can find our y. If you plug everything into the calculator, what are we going to get? Well, we're going to get 8 times 7.5 plus 6 times 4, which is 24, plus 4 times 0.5, all of that divided by 8 plus 6 plus 4, and that's going to be 34.8. So 34.8. I think I did something wrong, maybe? Yep, definitely did something wrong. I put 75 instead of 7.5. All right, so 4.78. So that's going to be 4.78 inches. Okay. Does that make sense, though? Well, let's think about it. If we looked at the centroid, we would expect it to be a little bit higher than the centroid of the central rectangle. And the centroid of the central rectangle is at 3 plus another 1, so it's at 4. So it makes sense about 4.78. So that at least agrees with intuition. Well, now that we found that, we know where our actual neutral axis passes. And I'm going to do it in this color. So right here, this is where our neutral axis passes. Now we want to find the moments of inertia. And so the moments of inertia are going to be about this axis. So I'll have to shift this one by this amount, and maybe that's not the right color. This one by this amount, this one by this tiny amount, and this one by this amount. So that's where you can make a lot of mistakes. So let's just be careful here, and let's just do I1. Well, what's I1? Well, I1 is going to be what? It's going to be 112 from the centroid of this specific shape 1, times the base, which is 8 inches, times the height, which is 1 inch. All of that is to the third. And then I'm going to add what? Well, I'm going to add the total area, which is 8 inches squared, multiplied by the distance. So that's where we might get confused, where I might get confused. So let me just be careful here. I know that my centroid of 1 is going to be at 7 plus 0.5. We have it right there, 7.5. I want to subtract where the centroid of the total shape is, and we said that that's 4.78. So that's how I'm going to find it. I'm going to do 7.5 inches minus 4.78 inches. And it shouldn't be too much of an issue. Sorry. Shouldn't be too much of an issue if you do everything from the same datum. So here, instead of calling it, I'll call it datum. If you do it from the same reference point, it shouldn't be an issue. So that's for I1. We can do the same for I2 and I3. So let me just create some space here, and we'll do that. For I2, that's going to be 1 over 12 times 1 inch times 6 inches to the third plus what are we going to have? Well, we're going to have the area, which is 6 inches squared, multiplied by the shift that we have to do. Well, we know that that was at 4, that the centroid was at 4, so we have to do, in this case, 4.78 inches minus 4 inches. And remember, that is squared. The distance is squared. Units are consistent now. We look at this one, and what are we going to have? Well, for the base, we have 4 inches. For the height, we have 1 inch to the third plus the total area, which is 4 times 1, 4 inches squared. And then I'm going to have to shift it up, not by 4.76, but by 4.76 inches minus where the centroid was, which is 0.5 inches. And so once I do that, I can plug these things into the calculator. So why don't we do that real quick and see what we get out of that. So I'm going to get 8 times 8 divided by 12 plus 8 times 7.5 minus 4.78, all of that squared. Let me see if I did this right. And that's going to be 59.54. Nope, 59.85. I got my calculator in scientific mode. 0.85. Inches to the fourth. Well, let's look at the second one. Well, that's going to be 1 divided by 12 multiplied by 1 times 6 to the third plus 6 times 4.78 minus 4, and all of that needs to be squared. And so we get 1.65 inches to the fourth. The last one is going to be 1 over 12 times 4 plus 4 times 4.78 minus 0.5, and all of that squared. And what we're going to get out of, what we're going to get is 73.61 inches to the fourth. Now the total, I total, is going to be the sum of these. So which we can add now because they are from the same reference axis. And so what is it going to be? Well, it's going to be 59.85 inches to the fourth plus 21.65 inches to the fourth plus 73.61 inches to the fourth. And so what we get is what? Well, let me do it. 59.85 plus 21.65 plus 73.61. And that's going to be 155 inches to the fourth. Right there. So now that we calculated that, I think we have everything we need. Because we're going to calculate the maximum stress and strain. Now, if this is going to have a load coming from here, which is what we see over here, then what we're going to see is that the top is in compression, the bottom is in tension. So I'm going to be expecting that, right? We're going to use the pure bending equation. So we're going to say that sigma at the top is going to be equal to what? Well, it's going to be equal to the minus of the total moment, which is 500 kips times inches, multiplied by the y. So the distance, this distance right here, from NA all the way to the top. So from NA to the top, well, we know NA is 4.77, and we know that the total to the top is from our datum is 8. So we got to do 8 minus 4.78. So 8 inches minus 4.78 inches, and all of that is going to be divided by 155 inches to the fourth. And we're going to do the same for the bottom. Now notice how at the top we said it was in compression. In fact, we have a positive y term, so the negative is going to stay. At the bottom, we're just going exactly negative 4.78 inches down. So the 4.78 is basically acting as a shift, if you know what I mean from shifting functions. And so now we can plug everything in and see. And this is the moment where I usually get frustrated because I do this long reasoning and I feel like I'm on the right track and then I get the wrong answer. But I guess it's a journey. All right. So we get negative 10.39 here. Negative 10.39. And we have KSI, and so we specify that this is in compression, put a box around it, make the teacher happy. And now we do the same at the bottom, and we're going to get a positive value of 15.42. 15.42 in tension. And so right here, and so this is how to approach this problem, or how I would do this problem. If you know what you're getting into and you do it fast, then perhaps you can shave off some time, but you need to understand how it works first. I hope this was useful, and I'll see you next time.